Okay, welcome back to Engineering 255 Statics. We are looking at the last video of the chapter 2, and this is a topic about the dot product. This is a spatial operation of the vectors, and we will see how it can be used in the force vector. So the objectives is to determine an angle between two vectors, and we are going to use that information to determine the projection of a vector along a specific line. Let's look at what this is about. To give you an idea why we need the dot product, let's use this example. So suppose you apply a force and you use this force on a wrench at the point of A. So this is the point of A. Your hand is here, this is the wrench, and you are pulling the wrench to this direction. We wanted to know what is the actual component that will help to turn the boat. Okay, so the reason that we wanted to do this is because when this force is not perpendicular to this the arm here, those forces are not going to help you to turn the boat. And this is what you learn in the physics. This is about the torque, right? Anything that is parallel, that is not perpendicular to the lever arm is not going to do anything to help to turn the boat. It will not provide a torque. So how do we do that? And what is the force actually perpendicular to that? So how do we find that? Let's look at the definition of the dot product first. So the dot product is between two vectors. If you have a vector A, you have a vector B, and our symbol to represent a dot product is simply put a dot in between these two vectors. When you do that, the result of the dot product is going to be equal to the magnitude of A, magnitude of the B, times the cosine of theta, where the theta is the angle between these two vectors. Look at this picture, shows you exactly what we mean. This is a vector A, this is a vector B, and the magnitude of A represents as the A here, and B represented here. Angle is between these two. This angle has to be between 0 and 180 degrees. Important thing about this dot product is this. It's the operation between two vectors. However, the result of this is a scalar. It's not a vector. So this is important that you need to know. The unit of the dot product will be the product of the unit of A and B. So if A is a force and B is a force, then the result of the dot product will be the force squared. However, normally we are not going to have that situation. One of the special situation that we wanted to consider is that if you have a two vector I and j, this g here is a typo, there should be a dot here. So if you have I dot product with j, which is like an x component, x direction dot product with j, what is the angle between these two, I and j? Is 90 degrees. And if you go back to the previous slide, that what is our definition about dot product? It is going to be the magnitude of I times magnitude of the j times the cosine of the angle, which is going to be 90 degrees. And what is cosine 90 degrees? Cosine 0 is equal to 1. Cosine 90 is going to be equal to 0. So when they are perpendicular to each other, their dot product is going to be equal to 0. However, if they are parallel to each other, then the dot product will be equal to 1. So I think because there's some typo in here, I will say this one is going to be dot here. But when you look at this one, this should be like I with I. This is not going to be J. This should be I dot with I. Okay. It's going to be hard for me to do that here. Okay. Anyway, so if the vectors are parallel to each other, when you do the dot product, the result is going to be the magnitude product. Okay, there's no cosine. That's going to be cosine 0, and that will be 1. So if you have vector A, you have vector B, we can represent each one of the vector as a component like this, Again, this G here should be a dot here. This should be the dot product. This should be a dot product. So you have A dot B is equal to this, represented as the Cartesian form dot product of the B Cartesian form. And the result is going to be this one multiplied with BI, right? AX BX I times dot with I, which is equal to 1. If you use AXI dot product with BYJ, then you have I dot product with J that's equal to 0. So you have nothing about I with a J. You have nothing about I with K. Therefore, the result is going to be only multiply with the same component direction, that is the AX times BX, AY times BY, AZ times BZ. So it's very simple to do this kind of dot product. You just simply need to multiply the amplitude at the same direction, and that is the dot product result. So how do you use the dot product to determine the angle between two vectors? It's a kind of a different way to look at the equation. Before we're looking at what is dot product definition is, it's simply just A dot B equal to A magnitude times B magnitude cosine angle, where the angle is the theta, right? Now, if we want to find the angle, then you think about, oh, A dot with a B equal to the amplitude. Let me put an arrowhead here. A and B cosine theta. So we move these one to this part here and take up cosine, we got an angle, right? And that is this one right here. So to find the angle, we simply just find A dot B. And what is A dot B? Is going to be the component at the same direction and something together. And divide by the amplitude of A, divided by amplitude of the B, you got the cosine up cosine and get the angle. The other thing we might try to find is that how do we find the projection of the vector? And this will come back to the first example that we show you, the application of the dot product. You have a range, you apply a force, and the force is the angle. The force, how do I know how much force actually will give us some effect to turn the boat, right? So only when the force is perpendicular to the lever arm. So if I can find out how much of the force that is perpendicular to the lever arm, and then we'll be able to find out what is the force actually make the contribution to that application. So if you know what direction is perpendicular to the arm, and let's just say AA here is the direction that is perpendicular to the level arm. And we use of A to represent the unit vector of the AA. And what is a unit vector? It's a vector with a unit of 1, and direction is on this direction. So this one will help us to find out how do we decompose that. So here we put A sub P represent how much of the A is projected along this line, which is the AA line here. We simply use the vector of A with the dot product use of A to get the projection. So this is what you are going to get if you find out these two is going to be the projection of the A along the line of AA. So it's very simple. So how do you do that? First you need to find this use of A, right? Because normally this A is given. You need to find out the unit A, which is this direction. Now in this example it's horizontal, but in a lot of cases it's not going to give you like this perfect situation. You have to find out what is the AA direction, and a lot of time you are going to find a position vector, because the position vector help you to find the use of A. Remember, how do you do that? Unit vector is equal to position vector divided by the amplitude of the position vector. That is the unit vector. So determine the projection of the vector. You find the projection by using the this is the position vector. This is the position vector, and this is the projection which is coming from the dot product, and this is the unit vector of that direction. Let's use an example to explain how we apply those. In this example, we have force acting on the hook at point A. So this is the point A, right? And the force that we have is this force right here. Use this one. So this is the force, and they give you the direction, right? So this is a force vector itself. This K here is not the unit vector. This K here represents 10 to the 3, that's 1,000 Newton. So it's a negative 6,000 Newton in the I direction, 9,000 in the J direction, and 3,000 in the K direction. We want to find out how much of this force actually is along this line here, from A to O, along this one here. So what we really want to find is how much of this force actually project to this line. When you project, meaning what is the perpendicular component that is along this line here. So how much of this is going to be along this line here. And the first thing we do is actually to find an RAO. It's from and to. This is important. A lot of people probably use O to A. This is wrong. Where you apply the force is going to be your starting point. So you use RAO. RAO. So what is RAO equal to? It's going to be the O coordinate minus the A coordinate. And look at O coordinate here. O coordinate is the origin. So this is the origin. What is the A coordinate? A has an X component, which is this much. And no, this should be this much here. Yeah. So this much is 1, right? So we have 1. How much is y? Y is from here to here, which is negative 2. It's on the opposite direction. How much is z? Z is going to be this much, which is 2. So it's 2 here. Right. Okay. Once you have this R, and then we can find out the angle, and we can use the projection by using this. Again, this G here should be a dot product. Here, this one should be a dot product. So the angle is going to be up cosine of the F dot RAO divided by the magnitude of AF and times the magnitude of RAO. How do you find the magnitude of F? It will be coming from here. You will be negative 6,000 square plus 9,000 square plus 3,000 square and square root of the sum of these three. So let me show you what the result looks like. So you got RAO equal to this. Remember how we find that? By using the position vector of O minus position vector of A. O is 0, 0, 0. A is 1, negative 2, and 2. And yeah, so that's what this one looks like. You got RAO is equal to 3. This is the length of this one here. This is the length of this one. The F is this one here itself, so it's given. And we can find out the magnitude of the F by taking 6,000 squared, 9,000 squared, 3,000 squared, take square root of that, which is equal to this much. Then you do a dot product. So this should be a dot here. F dot RAO. How do we do dot product? You take the same component multiplication. So minus 6 times minus 1 is this one here. Then you have 2 and 9. You have 3, negative 2, 3, negative 2. You sum them together. This is the dot product of these two. Once you have dot product, you can find the angle, which is going to be cosine, up cosine, dot product divided by the amplitude of each one. You got this angle. So this is the angle, which is this angle that we try to find. And if you want to find how much force is along this line here, right, then you need to find the unit vector of RAO, and we just show you that RAO vector divided by the magnitude of itself is going to give you a unit vector of, this is the RAO is the position vector, right? Unit position vector divided by the magnitude of the position vector give you the unit vector. You times the force vector, you do the dot product of that, give you the projection. So the projection is equal to 6,000. And again, position vector is a scalar. It doesn't have direction. And that is the result of this example. Okay, so this is the end of the chapter 2. In the class, we're going to have some more example. Remember these. In the lecture, we are going to give you one test. It's going to be like an in-class activity. It will be graded, and so make sure that you understand this concept. The in-class exercise will be something that we mentioned in the video. I'll see you soon.